Hello dear students, welcome to mathematics class. In this class, let us discuss the example on group. So here it is the question. Show that the set of real numbers of the form a plus b root 2 where a comma b belongs to the set of real numbers is a group under addition. So here it is the question. Now let us solve this one. Let r is equal to a plus b root 2 such that a comma b belongs to the set of real numbers. So here let us consider this as r dash. R dash equal to a plus b root 2 where a and b are the real numbers. Now let us consider, let x equal to a1 plus b1 root 2, y is equal to a2 plus b2 root 2, z is equal to a3 plus b3 root 2. So here let us consider the three numbers x, y, z belongs to r dash. X, y, z belongs to r dash because r dash is the set of real numbers of the form a plus b root 2. And here x, y, z are in the form of a plus b root, and a1, a2, a3, b1, b2, b3 are the real numbers. So here x, y, z belongs to r dash, where r dash is the set of real numbers only, but the numbers of the form a plus b root 2 and a1, b1, a2, b2, a3, b3 are the real numbers. And now we need to prove that r dash is the group. Now to prove r dash is a group, that we need to prove. So for proving r dash is a group, we must satisfy the four properties: closure property, associative property, identity and inverse. So first of all let us prove the closure property or closure law, right? So for that, the general statement is for all a comma b belongs to G, it implies a star b belongs to G. So it is the general statement of the closure law. But here x, y, z are the elements. Let us consider x comma y belongs to r dash. We need to show that x plus y is also in r dash. So here consider x plus y, where x equal to what? a1 plus b1 root 2, right? And y is equal to a2 plus b2 root 2. So here x plus y is the sum of x and y, that is a1 plus b1 root 2 and a2 plus b2 root 2. It is equal to, now collect the like terms one side, means the numbers which are not multiplied by root 2 and which are multiplied by root 2. So therefore a1 plus a2, these two are not multiplied by root 2, plus b1 plus b2 root 2, because b1 and b2 are multiplied by root 2. Now here we can consider these numbers as a dash plus b dash root 2, right? Where a dash equal to a1 plus a2 and b dash equal to b1 plus b2. So therefore here a dash plus b dash root 2 is of the form a plus b root 2, right? So therefore it implies that x plus y is also the element of r dash. Hence we can write for all x comma y belongs to r dash, it implies that x plus y belongs to r dash. Hence closure law satisfied. Closure law satisfied for r dash. Then the second law is associative law. Associative law. So here we need to consider the three elements x, y, z belongs to r dash, and we need to show that x plus y plus z is equal to x plus y plus z. If we prove these two are equal, then we can say that associative law satisfied for r dash. Now let us consider LHS, that is given by x plus y plus z. So here substitute the values for x, y and z. X equal to what? a1 plus b1 root 2, y is equal to a2 plus b2 root 2, and then z plus a3 plus b3 root 2. So here also we need to take like terms one side. So here a1, a2 and a3 are not multiplied by root 2, plus here b1 plus b2 plus b3 root 2, because all these three are multiplied by root 2. So it is our LHS, simplified form of that x plus y plus z. Then RHS is equal to x plus y plus z. Again x equal to a1 plus b1 root 2 plus here y is a2 plus b2 root 2 plus z is a3 plus b3 root 2, right? Then here a1 plus a2 plus a3 plus b1 plus b2 plus b3 root 2. So therefore here LHS and RHS are giving the same output, so it implies that LHS is equal to RHS. It implies associative law satisfied, right? Associative law also satisfied. Then we need to move towards the identity law. Third one, identity law. So for identity law, we know that if addition is the binary operation, then 0 is the identity element, and if multiplication is the binary operation, then 1 is the identity element. Here the given binary operation is addition, then we can say that 0 is the identity element. So here addition is the binary operation. Addition is the binary operation. Therefore 0 is the identity element. 0 is the identity element. Now the given set is R dash, and in R dash all the elements must be of the form a plus b root 2. But here 0 is the identity element and this 0 must be in R dash. So therefore we need to show that 0 is also in R dash. Now here we can write this 0 as 0 plus 0 root 2. 0 plus 0 root 2, which is of the form a plus b root 2, right? This 0 plus 0 root 2 is of the form a plus b root 2 with a and b is equal to 0. So therefore 0 belongs to R dash. Hence it implies that identity law satisfied. Then fourth one, inverse law. Inverse law. So here for all x belongs to R dash. So here R dash is the set of real numbers of the form a plus b root 2. Since it is a set of real numbers, both negative and positive real numbers will be there in the R dash. So therefore here x belongs to R dash, it implies that minus x is also in R dash, such that x plus of minus x equal to minus x plus x equal to 0, which is the identity element, right? So let us verify for the particular value of x. So here x equal to what? a1 plus b1 root 2. This belongs to what? R dash. It implies that minus a1 minus b1 root 2 belongs to R dash. Then we need to verify the condition that x plus minus x and minus x plus x. So here it is a1 plus b1 root 2 plus minus a1 minus b1 root 2 is equal. Here we can write a1 minus a1 plus b1 minus b1 root 2 by collecting the like terms one side. So it implies 0 plus 0 root 2, which is the identity element of R dash. And similarly minus a1 minus b1 root 2 plus a1 plus b1 root 2. It is a Sanket condition that minus x plus x. So it is equal to minus a1 plus a1 plus minus b1 plus b1 root 2. It is also equal to 0 plus 0 root 2, which is the identity element of R dash. So therefore we can say that minus x is the inverse of x, right? Because after adding minus x to x, we are getting the identity element. So therefore this minus x is the inverse of x. It implies inverse law satisfied. Inverse law satisfied. So therefore here we have satisfied all the 4 laws of the group, the closure law, associative law, identity law and inverse law. Therefore the given set R dash under the given binary operation addition is a group. So it is the first example. And next example is, this one is the second example. Show that G is equal to cos theta plus I sin theta, where theta belongs to the set of real numbers, is an abelian group. Is an abelian group under multiplication. So here we need to prove that the given set G is equal to cos theta plus I sin theta, where theta belongs to R, is an abelian group under multiplication. To prove that G is an abelian group, we must satisfy the 5 laws. One is closure law, associative, identity, inverse, and in the addition of commutative law. So if 5 laws are satisfied for G, then we can say that G is an abelian group with respect to multiplication. So let us solve this one. Let G equal to cos theta plus I sin theta, where theta belongs to R. Then G can be written in short form as cis theta, where theta belongs to R. That cos theta plus I sin theta. In short form it is cis theta, that is cos, C for cosine, I is the imaginary part or imaginary number, and S is the sine. So therefore cosine plus I into sine. Now let us consider the 3 numbers. A is equal to cis theta 1, B equal to cis theta 2, C is equal to cis theta 3. So here A is equal to what? Cos theta plus I sin theta 1, B equal to cos theta 2 plus I sin theta 2, C is equal to cos theta 3 plus I sin theta 3. So here A, B, C are the elements of G, and theta 1, theta 2, theta 3 are the real numbers. So it is our consideration. Now let us move towards the proof. So first we need to satisfy the closure law. First one, closure law. So here the general definition or the general statement: for all A comma B belongs to G, it implies A star B belongs to G. So here the star is multiplication. Then we need to prove that A into B belongs to G. Now consider A into B, where A is cis theta 1 and cis theta 2. Cis theta 1 into cis theta 2. So let us expand this one. So it is cos theta 1 plus I sin theta 1 into cos theta 2 plus I sin theta 2. Now multiply this one. Cos theta 1 into cos theta 2, cos theta 1 into cos theta 2 plus cos theta 1 into I sin theta 2, that is I cos theta 1 sin theta 2 plus I sin theta 1 into cos theta 2. Then I sin theta 1 into I sin theta 2, that is I into I square, which is equal to minus 1. So minus of sin theta 1 into sin theta 2. So therefore here cos theta 1 into cos theta 2 minus sin theta 1 into sin theta 2 plus, then let us take that I common from these two terms, that cos theta 1 sin theta 2 and I sin theta 1 into cos theta 2. So let us write this as sin theta 1 cos theta 2 plus cos theta 1 sin theta 2. So here cos theta 1 into cos theta 2 minus sin theta 1 into sin theta 2, that is cosine of theta 1 plus theta 2 plus I into, here this is sine of theta 1 plus theta 2. So these are by using the identities that sine of a plus b and sine of a minus b. Sine of a plus b is sine a cos b plus cos a sine b, and cos of a plus b is cos a cos b minus sine a sine b. So therefore this can be written as cis theta 1 plus theta 2. So here in the given set G, all the elements of the form cis theta, right, where theta is the real number. So therefore here a into b becomes cis theta 1 into cis theta 2. Then after simplification we got cis theta 1 plus theta 2, where theta 1 and theta 2 real numbers, then sum of them is also a real number. So therefore cis theta 1 plus theta 2 belongs to given set G. Therefore we can write that for all a comma b belongs to G, it implies a into b belongs to G. Hence closure law satisfied. Closure law satisfied. Then next, second law is associative law. Associative law. So here to prove the associativity we need to prove that for all a, b, c belongs to G, for all a, b, c belongs to G, we need to prove that ab into c is equal to a into bc. So for that consider LHS, that is ab into c, where a into b is equal to what, that in proved that closure law, a into b is equal to cis theta 1 plus theta 2, right, that is cis theta 1 plus theta 2. So it is a into b, and c is what, cis theta 3. And if we expand as in the closure law, we get cis theta 1 plus theta 2 plus theta 3. Here you have to write cos theta 1 plus theta 2 plus I sin theta 1 plus theta 2, and here cos theta 3 plus I sin theta 3, then multiplying, then separating the like terms, you will get cis theta 1 plus theta 2 plus theta 3. And similarly LHS, sorry RHS, in RHS there is a into BC, where a is what, cis theta 1, b into c, b is what, cis theta 2, it is cis theta 3 is equal to theta 1, and cis theta 2 theta 3, that becomes cis theta 2 plus theta 3, and it is equal to cis theta 1 plus theta 2 plus theta 3. So therefore here we can write LHS equal to RHS, because here LHS we have cis theta 1 plus theta 2 plus theta 3, here also same thing. Then it implies that associative law satisfied. Then third one, identity law. Identity law. Here the binary operation is multiplication. So under multiplication, 1 is the identity element, right? 1 is the identity element. So that we can write in the form of cos theta 1 plus sin theta 2. So here 1 can be written as 1 plus 0i, right? 1 plus 0i, because imaginary part is completely 0 because 0 into I is equal to 0, then remaining only real part, that is 1. So here, for what values of theta cosine becomes 1, that we know that cos 0, right? Cos 0 is equal to 1 plus I into, and we know that sine 0 is equal to 0. So therefore here cos 0 is 1, that becomes the real part 1, and sine 0 is equal to 0 into I is there, that is I sine 0. Now this belongs to G because 1 must be expressed in the form of cos theta plus I sine theta, then only that is in G. Therefore the identity element E is equal to cos 0 plus I sine 0. It implies identity law satisfied. Then the fourth one is inverse law. So here the general statement of the inverse law is, for all x belongs to G, there exists x inverse belongs to G such that x star x inverse equal to x inverse star x equal to the identity element E. Then here the numbers are of the form cos theta plus I sine theta. Then we need to find the number in the form of cos theta plus I sine theta, which is giving the product as 1, right? Let A belongs to G, that A is equal to what? Cos theta 1 plus I sine theta 1 belongs to G. Now here consider A inverse. Consider A inverse, that as cos theta 1 minus I sine theta 1. So here also it is in G because the elements of G are in the form of cos theta plus I sine theta, where theta is the real number. If theta becomes minus theta, then sine theta becomes minus sine theta. So therefore here let us consider A inverse as cos theta 1 minus I sine theta 1. Now check whether the given condition will satisfy or not. Let us consider A into A inverse. A is equal to what? Cos theta 1 plus I sine theta 1, and here cos theta 1 minus I sine theta 1. If the product is equal to 1, then we can say that cos theta 1 minus I sine theta 1 is the inverse of cos theta plus I sine theta. So here it is of the form A plus B into A minus B, which is equal to A square minus B square. A square is what? Cos square theta 1 minus B square is I square into sine square theta 1, which is equal to cos square theta 1, I square is minus 1, minus into minus becomes plus, sine square theta 1. By using the trigonometric identity, we can write this as equal to 1. So therefore we can say that A inverse equal to 1. It implies that cos theta 1 minus I sine theta 1 is inverse of cos theta 1 plus I sine theta 1. Hence we can write, for all A belongs to G, there exists A inverse belongs to G such that A into A inverse equal to A inverse into A is equal to 1, which is the identity element. Then finally we need to conclude the commutative law, that is the last property to say that the given group is abelian. So commutative law. Here for all A comma B belongs to G, we must satisfy AB is equal to B. So now AB is equal to what? Cis theta 1 into cis theta 2. So already in closure law we have proved this is equal to what? Cis theta 1 plus theta 2. Then B into A. B is cis theta 2 and A is cis theta 1, which is equal to cis theta 2 plus theta 1. And we know that addition is always commutative. Then this is cis theta 1 plus theta 2. Therefore AB is equal to BA. If AB is equal to BA, it implies commutative law satisfied. Commutative law satisfied. Hence, given set G along with multiplication is an abelian group. So therefore, in this class we have proved two examples. One is, so here this is the first example. Show that the set of real numbers of the form a plus b root 2 is a group under addition. And the second one is, show that G equal to cos theta plus I sin theta, where theta belongs to R, is an abelian group under multiplication.